All right, coolio. We're live then. So let me share my screen here and get right into the summary so we don't lose much more time. Because today will be a longer session than last time, I'm pretty sure. So today we're just going to talk about Chapter 2 and Chapter 3 in the Statistical Rethinking book by Richard McElraith and the second lecture on the YouTube lecture series. So basically what we're covering today is the basics of Bayesian inference and calculations and try to understand how Bayesian models learn. And for that, again, with a short summary of what I have taken from this, basically Bayes is, and I really liked how McElraith put that in his lecture, Bayes is just counting in a fancy way. And while I really like that for how simple it sounds, I also dislike it for how laborious it sounds, because it sounds as though it doesn't scale well with sample sizes, and more on that later, thankfully. But I really like this example right here, which he brought up in the second chapter and the first video lecture, which he dubbed the Garden of Forking Data, where basically once you go down one path, you only have a certain amount of other paths to choose from, and other options are locked off for you. So in this example here, he has a bag with 4 marbles of 2 colors, blue and white, and he draws with replacement. So marbles go back into the bag once they've been drawn, the bag gets shaken, and you draw again. You then obtain a sequence of blue, white, blue, and you try to, from that, estimate what kind of proportion of blue and white marbles are in the bag. And you can then build this kind of garden of forking data right here, where you have, in this case, 3 different options out of 5 total options, which would be here, because you could have all whites, all blues, and any mixture in between. But neither all whites nor all blues make any kind of sense to obtain blue, white, blue, because you do need both kinds to be present. So then you can just walk through this path in this garden and count how many paths there are per garden, meaning per specification of what could be in the bag. So that's our conjecture or our model having some assumptions. The assumption here being, for the first one, that we have 1 blue marble and 3 white marbles, which corresponds to this part of this big plot here, where you can see we really only have 3 paths to go down on, and that is, first marble we draw is blue, then we can draw 3 white marbles, but then on each of those paths, we only have the 1 blue marble to draw. So that leaves us with a total of 3 ways to produce this sequence, having 1 blue marble and 3 white marbles. And you can then write that out for all of the other combinations, and you can see that with 3 blue marbles and 1 white marble, you get the most ways in which you could produce the sequence of blue, white, blue, which should be quite intuitive because we see more blues in the sequence that we pulled. So we would also assume that there are more blues in our actual data. So in our marble bag, that is. Now, you can do this for everything that you have, at least in these binary settings. You can draw these different paths, but it gets very complicated very fast, so it doesn't scale very well, at least if you do the visual interpretation of it. Because now if you add another draw from the bag, so this is just 1 more blue marble, you now need to not draw all of these things again, but you can take the previous counts that you already had, 3, 8, 9, and 0 and 0 respectively for the extreme examples, which we're not interested in. Or we would be interested in if they made any logical sense, but they don't, so we just forego them here. And you can then see how many ways are there to then, on top of this, because we're sampling with replacement, everything goes back into the bag, to obtain 1 more blue marble. And in this case, that is 1 way to obtain another blue marble on a random draw if you have 1 blue marble out of 4 marbles, 2 if they're exactly even, and 3 if there are 3 blue marbles and 1 white marble. And you can then just multiply that with the already existing pathways, because that gets added on top of the outer ring that you can see here in the right-hand plot. That's why you multiply it, because for each of these blue marbles that you can see here, another however many paths are noted down here appear. And that leads us to now even more strongly believe that there has to be a majority of blue marbles rather than white ones. Because we have, in fact, sampled 3 blue marbles and 1 white marble. And we only go through the sequence in which we have sampled them so we can visualize this much easier. The sequence doesn't actually play any role. Irrespective of which sequence we sample them in, we would always get to these counts right here. So comparing all possibilities that we get from counting all of these different paths enables a selection of the most plausible model or assumption. So what we do here, and I think this was stressed really, really well in the reading materials for this week, was that we don't identify a true model, because no model is ever true. There's always going to be a bit jittery stuff in the data, which no model can ever account for. So there's always going to be inherent stochasticity. However, what we try to find is the most plausible model. And for that, we can just compare all of the different possibilities in these Bayesian setups quite well. Now, the next step in Bayes, which I think if I remember correctly, Gregor, you were quite interested in, is how to add prior information to this. And with the marble example from the lecture and the book as well, we could obtain some information of how many types of these bags are produced each. So for example, for every batch of 6, there may be 3 bags produced with just the 1 blue marble, 2 bags with exactly 2 blue and 2 white marbles, and then 1 bag which contains majority blue marbles and just 1 white marble. Now, with that in mind, we can change the probability of our bag being of a certain kind, because now we have drawn our samples, which led to these prior ways, that's our prior information, but now we've obtained additional information. And instead of looking at these in solitude by themselves, instead of saying, well, with a 1/2 chance, because it's 3 out of 6, we have a bag with just 1 blue marble, we can multiply the factory count and the prior ways that we identified on the previous slide here to get to an improved understanding of what the actual probability is, or likelihood that we have a bag of a certain type. For that, we just multiply them, and we can see now, because it is so much more likely that we have an exact even split of marbles than a majority of blue marbles, we now get pushed into a count at which we would argue that it is most likely for us to have a even split of marble types in our bag, even though we drew way more blue marbles than we did white marbles. And that's because we combined information. So the big thing here is that adding prior information to our data can greatly improve our understanding of the world. The big question that follows from this, and the chapters didn't quite answer yet, but I'm sure we'll get there in the material that we're going to go through, is what do we do when we don't have prior information? And then you usually go into, from my understanding so far, and please interrupt me if you already know more than me on this, from my understanding, you then just use uninformative priors, but McElraith in the book argues that that is usually not a good practice, since we most of the time can infer at least something meaningful about our prior expectations. And I'm sure we'll cover more of this.
So it's exactly as you said, like you will probably never you will never experience a situation where you don't have prior information on any setting. So an uninformative prior is more or less useless because you know something about it.
Yeah, thanks for weighing in there. Also, I would assume that using an uninformative prior, you usually just get to the same conclusion as you would with frequentist analyses. So making good use of a prior is highly important in Bayesian analysis.
Not only that, but like frequentist analysis often criticized Bayesian statistics because because Bayesian statistics are using priors, and it seems a bit like subjective.
Mm-hmm.
But frequentist statistics use priors as well. They just don't know it. And it's so much powerful to have this knowledge, I think.
Yeah, the priors of frequentist statistics are contained, to my understanding, in the frequency distributions that you compare your effects to.
Exactly.
I thought of it that way.
Yeah.
That's a good connection.
All right, moving on. Because raw counts themselves aren't necessarily the most important to us, because we would like to weigh stuff up against one another. And for that, we would usually standardize variables and their values, for example. But as far as Bayes is concerned, comparing absolute numbers is difficult and potentially not very informative. So what we can do is we can multiply a certain plausibility, or likelihood that is, with the counts that we have, which would then allow us to compare probabilities or plausibilities, which makes understanding of how something comes about much easier in comparing different model outputs. So with that out of the way, we know how the counting works, but how do you build an effective Bayesian model? So for this, McElraith suggests these 3 steps, which to my mind are very much the same as in frequentist statistics, because first you design a model, then you, in this case, condition on the data, or as he calls it, update, which you can do with grid approximation, quadratic approximation, or Markov chain Monte Carlo MCMC samplers. There's also Gibbs samplers, which I think are something else than Markov chain Monte Carlo, but I'm sure he'll go much more in depth on this. And if he doesn't, I know that the Introduction to Winbugs book that I'm reading at the same time as this goes into more depth on this. So I'll just input that at a later point when we get to these thingies. Then finally, you evaluate the model, critique it, and go back to designing it, which is this iterative process of building a model. And that is very much the way that I see frequentist statistics quite often too. And if you don't go back to see how well your model works and then potentially update it, I would argue that your model building is a bit flawed, whether you do it in a frequentist way or in a Bayesian way. It's just that Bayes allows you to do that a bit more easily using prior and posterior distributions. So I try to, and this is where my obsession with flowcharts comes in. I try to put all of this in a flowchart, and I hope you stick with me for this, because the first step is just to get our variables and make some assumptions about the causal relationship between the variables. We then use these to build a joint prior to get a better understanding of what we expect. We then feed this into our actual model, which we now condition on the data using the Bayes theory, which we'll get into with the practicals today. And for that, the conditioning works as Bayesian updating. So what sprung out to me here in the lecture was that every posterior is a prior for the next observation. And if we think about this in very crude terms, it is basically going through every observation each, taking the prior that we put in the first place for the first observation as a prior, shifting that prior around a bit, moving on to the next iteration, using the now updated prior in the first step as the prior for the second step. So one posterior of one step becomes the prior of the next step. And we iteratively update our posterior distribution. Now, this doesn't make much sense for really large data sets because it's like writing a super big for loop, which takes a long time to finish. But a few things to point out here is that the more observations you have, the heavier is the weight of the prior upon each new data iteration. Meaning if you already have, in this example on the right-hand side, 1,000 data points, and then you add another data point, that one final added data point won't be able to shift the posterior distribution around by a lot, because the distribution is already very set in its ways. So in Bayesian statistics, you don't have to keep track of your sample size as you have to in frequency statistics. You still might want to know your sample size, of course, but between Bayes being exact for every sample size that you can feed it to, because it doesn't suffer from the asymptotic maximum likelihood restriction, the sample size is already inherently contained in your posterior distribution, so it doesn't get lost along the way. And also, something I mentioned earlier when I said you could reorder the different paths in our garden of forking data, the order in which the observations are viewed does not matter, which comes with the assumptions of independence of observations, which may not be true, but that is then down for you to evaluate your model and critique it. So this is robust to order, as long as we can actually infer independence of the observations here. Now, the conditioning you can do with, and here I just made a really quick summary of this. I hope the book will go into more detail on this. And if it doesn't, then I probably will using the other book. With the conditioning, we can use three processes that McElrath has shown us in the book and the lecture. So there's grid approximation, quadratic approximation, and MC-MC samplers. All of those are applicable in different settings. So grid approximation, for example, only works for a few parameters, because what this does is it calculates the posterior distribution or distributions, so for each parameter, one distribution, at regular intervals that we specify. Usually we specify pretty fine intervals. However, as soon as we get more than just a few parameters and we need to calculate the grid approximation for all of their posterior distributions, it becomes computationally way too expensive. And the function just breaks. Well, it doesn't break, it still works just fine. I misspoke there. It just takes way too long to finish. On the other hand, we've got quadratic approximation, which models the unified posterior which models only unified posterior distributions. So from what I got from this, and I'm not quite sure if I interpret this correctly, so please jump in if you have a different thought of this. He said that these approximations don't work out with really complex models where you don't have unified posterior distributions, which to me sounds like you have posterior distributions which you cannot combine with one another. And I don't quite know how that would work, because I would argue that you can always combine distributions, but maybe my maths background isn't strong enough here, or I'm just blanking. But if we put this into words, the quadratic approximation works in such a way that it moves along the posterior distribution in sample steps, find the peak of the posterior distribution, and then assuming that the peak here is Gaussian, so it has a bell shape, and that might be one part where it fails if it doesn't have that bell shape, we calculate the slope and standard deviation around that peak to get a better understanding of the posterior distribution without having to create the entire posterior at once. Now, the last one that McElrath mentions is the Markov chain Monte Carlo method, which should be, from my understanding, applicable to all models, but it does work a bit as a black box. So for smaller models, you might be better off with the grid approximation because you can understand better what's happening. And what you do with this one is that you calculate random samples of the posterior distribution and then build a consensus of that distribution from those random samples. Meaning you can draw samples and then take out the bias from every individual sample by averaging them out over each other, which I think is very elegant because it also replicates very well what we have done with our study setups, because we somewhat randomly get observations from the natural system that we try to understand with our sample data.
Is that similar to bootstrapping? Just
from my understanding, yes.
This sounds very similar.
Yes.
Okay.
Gregor, do tell us if you have an improved understanding of this, and you can tell us if it's wrong or right. But from my understanding,
it's basically bootstrapping.
Right? Cool.
Bootstrapping from a model estimate here.
Yeah.
So that's one of the reasons why frequentist statistics is so successful in the past, because as you might guess, grid approximation has its limits. You know, like you said, it's very simple, and for me, it's perfect for learning the way to make estimates. Quadratic approximation is basically, yeah, like you can use it in frequent statistics as well. I think it's then the plus approximation called. Correct me if I'm wrong.
I think so.
Yeah, and both of these are just like they're limited. Like you said, grid approximation only a few parameters. Quadratic approximation has the assumption of a normal posterior, and MCMCs where they're just computationally quite exhaustive. So people in the past were not able to use them, and we're a generation who are able to use them. And I think this is awesome.
Yeah, couldn't have said that better myself. Thank very talented engineers for high computational power that we have.
Absolutely.
All right, moving on back to the flowchart. Now that, by the way, I am loving how much more we are interacting with the summary this time around. I hope we keep that up for the next few sessions. Now that we've conditioned our data, we've conditioned our model on the data, it's time to evaluate the model by looking at the joint posterior. And for that, there are different outputs that we may want to choose to analyze. A few of these we're showing right here. So model outputs are always built on the samples from the posterior distribution. You do have access to the entire posterior distribution, but you might usually want to just represent it with a few samples. And by a few, I mean multiple thousands. So you're quite sure of what you have. And the way to represent this is foregoing, and I have argued for this previously already on frequentist statistics, foregoing point estimates, because they are inherently less information heavy than intervals. For example, when you have a frequentist model, it really pays to report a confidence interval over just a point estimate. But once we go Bayes, we can even move beyond the confidence interval, because the probability, the way Bayes handles probability is much more intuitive and in line with what we would expect a confidence interval to do, which it doesn't. So what we can do to summarize these posterior samples is to look at percentile intervals, for example, where an equal area falls in each tail, and the weight or area covered by the percentile interval is what we specify. Another thing we could do is to look at the highest posterior density interval, HPDI, which is the narrowest interval that contains the specified area, or as McElrath puts it, mass that we want. So in this example right here, which I find very nice for looking at this, the point with the highest density or the highest probability isn't actually covered by the percentile interval, but is covered by the HPDI, the highest posterior density interval. So looking at how these two intervals differ from one another can tell you a lot about how skewed your posterior distribution can be. And then it all becomes a question of which one to report and whether to even report intervals in that case, instead of just showing the full posterior distribution. So the takeaway from this is that distributions contain much more information than point estimates, but intervals can only be trusted when the model can be trusted. So if you have a huge difference in the intervals that you use, you might want to retrace what you've done and how your model is specified, because that usually points to a potential flaw in your model or your data, but usually it's the model. So with that, we are now at the point where we want to critique the model and see how it actually performs. And for that, we use a posterior predictive check. So what we do here, sorry, I just have to move around the window with the cameras of us a bit so that everything stays legible. So the way we assess how this works is with predictive checks. So you can take all of the different samples from the posterior, merge them into one posterior predictive distribution, and then feed simulated data, for example, and see how well this now coincides with your predictive posterior distribution. Because with this, we can see how good the predictions actually work. We can check model assumptions, and we can do this iteratively to see how much better we might be getting by updating our posterior using new priors. And all of this sounds a bit confusing, at least to me it did. So I went to the Introduction to Winbug's book and looked a bit more at this, which this is actually still from McElreath, I think, and the next slide is from the Winbug's book. So when we draw samples from the posterior, we do so to check for a few things. The first one is model design. So we can sample from a prior as well as from a posterior to then get a better understanding of what the model anticipated, meaning the prior, and how those expectations were then altered by showing the data, which then leads to a posterior. And we can look at how much the prior has changed to the, how much the posterior has changed in comparison to the prior, which gives us an understanding of how well our model captures certain aspects of the data. Now, for model checking, we can simulate some implied observations to then check the quality of the model fit and the behavior, which is what I already mentioned on the previous slide, and something I do quite a lot for what I'm working with. I always like to come up with simulated data sets that have some implemented effects, and then I try to build a model that accurately rebuilds those effects, where my simulation of the data makes some inherent assumptions of how the model should work and how nature would express certain effects. And for that, we can use this step to check our model. Now, software validation is another one which came a bit out of left field to me because I often don't even think about this, but it's a very accurate point to right here simulate some observations with a known model and then attempt to recover the values of the parameters by fitting a model just to see if our fitting function works well. So for example, if we're not super well versed with R and we have to step into a different way of writing models, we might just, even when we're super sure that our model is correct, check if the software is working in the way we intended to. And for that, we would like to simulate and then sample from distributions. Another reason we sample or simulate observations is for research design. So we can simulate observations which lie in accordance with the hypothesis that we go in with to then evaluate how effective our research design is. This again comes down to what I already mentioned, where I'm trying to compare different methods right now with some data I'm simulating to identify the best research design for the question at hand with my simulated data. Sorry, I need to hydrate a bit, but the tea is still too hot. Another reason for why we just sample is to do some forecasting. So an applied prediction for some new observations that we use a posterior predictive sample for can help us forecast how our model would see the future, giving some novel observations by making use of the posterior predictive distribution, which are samples drawn from the posterior. And lastly, before going way too much into time on this summary here, why Bayes? And for this one, I stepped into the Introduction to Winbug's book, Now for Real, and they listed 6 reasons. The 6th one they listed was intellectual beauty, which I kept off of here because I don't want to make this too biased. But the first 5 made a lot of sense to me. The 6th one did too. I just think it was a bit too intense. So the reason we go Bayes is for numerical tractability. So we can fit super complex models, and Bayesian inference then returns estimates that are numerically close to conventional, meaning frequentist methods. This means that irrespective of how small or large our data sets are, Bayes is a really good choice to go with. The next one is absence of asymptotics. And this comes down to frequentist approaches often being fit with maximum likelihood or residual mean least squares error. I probably butchered that one. But this is where the exactness of Bayes at all sample sizes comes in. So the big takeaway from this for me was that Bayes can function just as well with small sample sizes as it would with ginormous sample sizes. But at lower sample sizes, you are really vulnerable to choosing plain wrong priors or very, very strong priors, because when you don't have a lot of samples, the prior has a lot of weight in determining the posterior. So your model might not change the prior distribution much when it transforms it into a posterior when you don't have a lot of samples. That being said, it is still exact and doesn't make assumptions of being unbiased as you near infinite samples, which maximum likelihood does. The next step, and probably most exciting for me right now, is the ease of error propagation. So you can compute the uncertainty of estimates, which is super easy because you just have a distribution. And then you can carry these distribution estimates of certain parameter values forward. Whereas this is much more difficult in frequentist statistics. And as a matter of fact, most people only work with point estimates, which really take away a lot of the information as to the uncertainty or the error around our point estimates. Because oftentimes what I have noticed is that when we, and me included, absolutely, don't see an uncertainty being recorded for a certain estimate, we assume that the certainty is 100%, which usually isn't the case. And our models should really account for uncertainty that is carried forward, even if it decreases our final statistical significance of the output, because that's just more honest science. Now, in addition to this, Bayes also offers a formal framework for combining information. And this comes down to informative priors enhancing Bayesian models, and that in turn allowing for the cumulative nature of science. Because one person might have a finding, and now to build on that finding, all we have to do is take the posterior that they obtained and plug it into our models as a prior, slapping our data on top as well as our model and combining the information into one, which I think is also the way forward for really interesting meta-analyses. Now, lastly, there's an intuitive appeal to this, and I'm sure we'll get into this when we look at the practice examples for this week in just a second here, because the probability in Bayesian settings can be interpreted very much as we would like to interpret probability in frequentist settings where we cannot do as such. So Bayes really lends itself much more to how we think about the world by virtue of just being humans. And that's the big takeaways of chapter 2 and 3 from my end. If you guys have anything more to add to this, then I'd be more than happy to hear that. Or if anything was unclear in here.
Just wanted to add that these summaries are plain awesome. Like I could listen to you all day. Thank you very much.
Well, since we have a recording, you actually can.
The Gill Sans
Thank you very
text,
much, so.
the text font, Gill Sans, always a good go-to.
I actually think that's an Aarhus internal font.
Is it?
I think it is, yeah. They probably took inspiration here. But yeah, I've got to say, I actually do not want to give away the summary task to anyone else, because writing the summaries helps me so much to conceptualize everything. It's seriously super useful for me. And with that out of the way, so this is the first time we're running practices. And I would just suggest, if that's fine with you guys, don't feel too much put on the spot. We could just go through the exercises. I start with exercise 1, Gregor takes over exercise 2, Sam goes on with exercise 3. If you haven't solved them, that's totally fine, and then we'll just skip you.
Oh, I haven't looked at it. I crashed last night.
Oh, that's totally fine. That's exactly what I'm saying. Don't feel put on the spot for this. because it's absolutely fine coming here and not having solved them, or having jumped some that you just couldn't solve. So I think today, if Gregor, if that's fine with you, if we just jump back and forth between the two of us, so we get different wordings and different explanations from different people, that might make for a more complete picture to anyone here right now and anyone listening to the recording. But if any one of you ever doesn't feel comfortable with that, just say it.
I'll have these all sorted for next time. Don't worry.
Coolio. And in that case, I am just going to restart my screen share here. And then I guess we're just going to bump back and forth screen shares between Gregor and I. And that might be a bit messy and we may come up with something better, but you know what? We'll leave that for next time. So what I've done here is I've just written an R Markdown file, which I translate into HTML. And I guess it would also pay to bring up the questions for this. I'm just going to read out the questions so I don't have to bring different windows back and forth, because then it becomes really messy, I would guess. So the first one is, which of the expressions below corresponds to the statement, the probability of rain on the Monday? And the statements, and I actually probably should bring it over here because it wants you to see something. And for that, I have to share the screen instead of the Firefox window. So I'm just bringing that over here. So question one is, which of the expressions below corresponds to the statement, the probability of rain on a Monday? And I actually think that two of the statements underneath here are true. So probability of rain doesn't include the Monday part. So we can already say, well, that's not it. The second one, I think, actually corresponds to this, because this is the probability of rain given that this is a Monday. A third one, again, doesn't fit the description because it is the probability of Monday given that it is raining. Now, the fourth one, I would say, also applies here because it's the probability of rain and it being a Monday divided by the probability of it being Monday in the first place, which should come out to the same thing as rain given that it is Monday. So that would be my solution to this.
You can keep that open because I'm...
Yeah, right. So we don't have to change the screen share here until we get to the coding questions.
So for the second question, which of the following statements corresponds to the expression PR Monday / rain? So the first one, I just tried to translate them into the expression. The probability of rain on Monday would be PR rain Monday. The second one would be the probability of rain given that it is Monday would be PR rain / Monday, or how do you call that?
That vertical bar?
Yeah.
Sam, do you know what to call that?
I just say given.
Yeah.
Given.
I honestly, I don't even know if that's correct, but whenever I see that, I just say given. Otherwise,
you know what? For the setting of today's session, it is given.
Okay. The third option is the probability that it is Monday given that it is raining would be PR Monday given rain. And fourth option, the probability that it is Monday and that it is raining would be PR Monday and so comma rain in as an expression. So option number 3 would be my solution for that.
I came to the same one here. So then question 3, which of the expressions below corresponds to, I didn't know my Steam was on, interesting. Which of the expressions below corresponds to the statement, the probability that it is Monday given that it is raining? And for that, we can just go through them again. So the first one is probability Monday given raining. Absolutely the case. Second one doesn't apply because it's rain given that it is Monday. Third one is rain given that it is Monday divided by the probability of Monday, which to my mind, should equate to the same thing as number one. So this, oh no, sorry, no. I've jumped the gun here. I think it's the next one. It's number 4 here. I made a typo. So the fourth one is probability that it is raining, given that it is Monday, times the probability that it is Monday in the first place, divided by the probability that it is raining, which should equate out to it's Monday, given that it's raining. Because this is just Bayes' theorem. That makes sense?
Yeah. Yeah.
You sure?
Yeah. I think. Oh.
I think it's helpful to have the Bayes theorem open to that question. Like it's hard to wrap. Like for me, it's really hard to wrap my brain around it.
Yeah, I think you're right. It flips them around in that first one.
Let's bring up a whiteboard for this one. Can I type on the whiteboard is what I want to know now. No, text. Come on, let me select text. No. Okay, for some reason it doesn't let me type, so please bear with my really bad hand drawing with a mouse. So you can see the whiteboard, right?
Yeah.
Coolio. So what we have is, oh no, that won't work. That really won't work. If that's a P, why can I not put text in? Is there something else I have to? No, it just doesn't let me select text. I can also not select stamps. That is weird. Clear all drawings. I cannot select text. Man, Zoom, if only you worked. All right, just taking this back, I am just going to open up a Word document here, and I'm just going to write in the screen shared Word document. It's going to be a bit less collaborative than if it was the whiteboard, but I guess that's fine. So, oh wait, no, my screen share is off. There we go. There's the screen share. So what we have is P rain. Actually, I can just copy that over from my other window. So what we have is this. And Bayes' theorem is basically, I may totally be getting this wrong now, because I'm still baffled every now and then. So it's basically the probability given the data. Oh, let's do this another way around. This is A, B, which then we can write as P, B, A. Come on, doesn't let me write anymore. There we go. PBA times, and now I often mix these two up. It's either times PB divided by PA or the other way around. Just quickly gonna look that up. Theorem, just to make extra sure. Yes, it's actually the other way around. There we go. That's the way it should be around. So what we want to know is, according to the question, just flashing this up here right quick, is the probability that it is Monday given that it's raining, right? Mm-hmm. For this, we would write P Monday given that it's raining, which equates to P of rain given that it's Monday. So I'm really just switching out A and B here for Monday and rain, respectively, times probability that it is Monday divided by the probability that it is raining, which is the exact same as we had in that one answer. So that's where basically what we wanted to know and what is, closed a bit too much there. Basically the answer number one here, Monday, given that it's raining, is the left-hand side of the Bayes theorem, with number 4 being the right-hand side.
Yeah, I'm with you.
Cool. All right. See Gregor nodding as well. Moving on from that, handing back over to you to 2E4, which is a very subjective kind of question, I feel like.
It is, yeah. The Bayesian statistician Bruno De Finetti, any Italian will kill me probably now, began his book on probability theory with the declaration, probability does not exist. The capitals appeared in the original, so I imagine De Finetti wanted us to shout the statement. What he meant is that probability is a device for describing uncertainty from the perspective of an observer with limited knowledge. It has no objective reality. Discuss the globe-tossing example from the chapter in light of the statement. What does it mean to say the probability of water is 0.7? So how I interpret it is that when you say the probability of water is 0.7, it's basically the best guess we can make given the data we have. So probability is just a language to express our uncertainty given our knowledge. This is how I would phrase it.
I think that's terrific. I went into a bit of a different route here, but I come to the same conclusion as you. So what I've written is, and I'm just going to read this out, completely uninformed and looking only at random samples, we would come to the conclusion that 70% of the Earth are covered by water. However, this estimate could be heavily biased once confounding factors are taken into account. Factors such as inaccuracy of the globe model we are tossing when compared to the real globe. So for example, the globe model is a perfect sphere, whereas the Earth is, I think, a flattened ellipsoid or something like that. So that might already put some bias into our understanding. So I think probability is a very theoretical thing, which we take to be granted and true about nature way too much. Because inherently what we're looking at, and with anything we're looking at, everything's a stochastic process. And there will always be aspects to a process which we just do not have control over, which we can't measure. And for that reason, exact probability isn't a thing. And I guess that is what the Finetti was after.
And also you can say 0.7 doesn't actually scale to telling you where the water is. In that example, you would just, if in pure data form, 0.7 doesn't tell you that there are oceans. It could be like spots of water all over the globe that you just happen to put your
but then you might get into arbitrary definitions of what do you consider to be an ocean and what's just a sea.
Crap.
So I guess as long as you just say 70% of the Earth is covered in water, you completely circumvent oceans, lakes, puddles, whatever.
Yeah.
So I really think this comes down to preciseness and accuracy with which we can look at the world.
Yeah, I'm with you.
All right, moving on to number 2, and this is where we actually get into plots. So I am now going to take you into my HTML solution for this here in a second. But first, let's try and understand the question here. So we recall the globe tossing example from the chapter, and we then compute, or it wants us to compute and plot the grid approximate posterior distribution for each of the following sets of observations. In this case, we're looking at a uniform prior for the observations water, 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 land, and then land, water, water, and so on. I don't need to read these out, I think. And actually, I answered this in tandem with question number 2 here. So I'm just going to cover that as well. I hope that's no issue, Gregor. Because for loops, just put for loops and for loops, and you can answer both of them at the same time. So what I've done here to answer the second question, I'm going to show you in a second. The second question is that we now assume a prior that is equal to 0 for any probability of water on Earth or any fraction on Earth below 0.5, and then constant at 1 for any p greater than 0.05. So that p here is binomial success rate, meaning water, no water, with water being a success. Then we compute and plot the grid approximate posterior distribution for each of these sets of observations from this example above. And that's why I just combined the two answers into one, because it's really just swapping out the prior. That's what I've done here, and there's definitely a more elegant way to this, no doubt. I create the three different data sets that we have. You can see my browser now, right? I'm sharing the screen instead of the application. Coolio. So I'm creating the three different data sets that we're looking at. I'm combining them into a list just so I have something to iterate over. Then I give them names just so I can combine that for some plot titles later down the road. For the priors, they actually need to be dependent on how many samples I draw for my P grid. That's why here I'm just writing down NAs and then I'm assigning them later down the road. I also assign some names here, again, just for plotting further down. And then I create a list within which I will plot, well, I will store all of my plots so I can then later combine them with a plot grid function from the cowplot package, just so I can get one unified output and not a mangled mess of plots just stacked by each other. Then I just write an easy for loop within which I say, for each of my data sets, please pull out the data set that we're currently looking at. We have this many observations in there, so that is our N. We have this many successes in there, that's our W count, so water. We now sample, in this case, just 25 grids. Could have made this 1,000 if I wanted to. Just went with 25 because that was in a solution I found online. Much of this I have just taken from a solution I found online and then understood it myself and reformatted it a bit so it works with how I code. And the link to where I found this is up here, just so if anyone's interested in this, and for the people in the recording who may have missed this earlier, all of these HTMLs are also in our folder, and Gregor has prepared some HTMLs of his own on his website, which you can also go to, and he'll share in just a second, I'm sure. So now that we have our grid sampler here, bless you, by the way, Gregor, we can now look at how many of these do we want to sample. So this is just the length of our grid, which of course is 25. So we could have just run with 25 too. But what we now do is we set our priors. Our first prior is just ones across the board. It's an uninformative flat prior. Whereas our second prior that we're looking at is that if it's below 0.05, we assume 0, and if it's above that, we assume 1. So then we step into another for loop, which just looks at the different priors. So for our first data set, we now look at the first prior, which is the uninformative one, or the uniform prior. Let's not call them uninformative, just uniform. We take our prior out, we build the density distribution, I'm sorry, I'm getting a lot of emails today. We take the density distribution that should be binomial because we're looking at water and land. We're doing this for however many counts we had in our first data set to start with. So this is 3 because we had water, 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 which is 3. We look at how many successes we get with so we look at the density distribution, binomial that is, for 3 successes on 3 trials with probabilities on our grid, which range from 0 to 1 in steps of whatever equates to 25 probabilities. That's what we're doing here. So that's going to be our likelihood. Because for all of these, we get a likelihood of how likely it is to get 3 successes in 3 trials when we have a probability of a success being whatever it is in that grid sample location. And we do that 25 times because we have 25 different P grid values back here. It's a vector with 25 values. And please stop me if I'm not making any sense anymore. We then just multiply likelihood times prior. Remember, our prior is just ones across the board for this uniform prior. The posterior is then the posterior which we calculated here, which is likelihood times prior divided by the sum of all of the values in the posterior. And what I then do is I just put it into a data frame, which I then feed into ggplot. So I'm not going to get into that right here because that's not what we're here for. And write that into my plot list. Then jump back to the prior selection. So now I'm looking at the disjunct prior, as I called it, zeros and then ones with a cutoff point at 0.5. And down here, I just plot the results. Where you can see if we only have successes, so only waters, the probability that the entire Earth is covered by water is pretty high. If we have pretty high counts of water, so this is 3 waters and 1 land, as you can see right here in the title, we have around a 0.75 peak, which makes sense because it's 3 out of 4, which is 3/4, which is 0.75. And if we have this mix right here, which I don't want to count out right now what this equates to, well, it is 2/5, which is less than 3/4, we do get this peak in the posterior density distribution more towards 0.5 than, well, less on 0.75 and moving towards the left-hand side of the spectrum. And as soon as we use these disjunct priors, we just get really strong jumps around the 0.5 mark of our density distribution, which shows us where the information of the prior that we fed into this actually comes in. And that's my big takeaway from this one. All right.
Thank you.
Cool. Welcome. That's what we're here for, right? Gregor, right over to you. Actually, could you, 1 second, I'm just going to open your website on my screen so we don't need to do the resharing.
Perfect.
Let me just quickly go open up the chat if I could find it. For some reason, it just doesn't want to show me the chat now. Oh, Zoom, how I love you. So I'm just going to take you on a weird trip throughout all of my virtual screens right now. I'm just going to bump that over there. And, oh no, now I've gone to chapter 3, where we aren't right now. So this is Gregor's website for everyone in the recording. Please hold your applause. And we go into question...
Sweet.
It's question 3, right? Yeah. Quickly going to flash the question text here and hand it over to you, Gregor.
Yeah, so the question is, suppose that there are 2 globes, one for Earth and one for Mars, and the Earth globe is covered by 70% of water, and the Mars globe is 100% land, so no water at all. Further, suppose that one of these globes, and you don't know which, was tossed in the air and produced a land observation. Assume that each globe was equally likely to be tossed. Show that the posterior probability that the globe was the Earth, conditional on seeing land, so so the probability of Earth given land is 0.23. So this was rather demanding.
Oh, you put it in here too. Sorry, I didn't see that earlier.
No, there's no like I didn't include the question.
Oh, sorry, but this is also already the next question, isn't it?
Is it Joe?
No. Oh, sorry. I got confused here. No, sorry, I got confused. I was already thinking of another one. Sorry, my bad.
Just let me wrap my hand around what I did there. It's quite some time ago.
I know what that's like.
Yeah. So, yeah, we start basically by defining a function that takes our priors and calculates our estimate, in this case, posterior interval, PI, because we want to iteratively apply this function to the sample sizes. No, this is a completely different question, isn't it? Let me just check. I think.
Yeah,
different.
I think you jumped something there, didn't you?
Let me just check my book.
Yeah. Oh, if you're using the physical copy, you might be on Statistical Rethinking version 1.
No, I'm on version 2.
Okay.
So we do 2 and 1. No, 2.
M3.
What was it? And 3. What the hell did I do?
Just gonna take a snack here. Yeah.
So that is
Gonna compare this with my stuff. Isn't that chapter 3 stuff?
I think so.
Yeah, because looking at my solutions here, that is chapter 3 M6, isn't it?
It is, yeah.
Yeah.
I'm sorry for that.
I think it may just be that. Oh no, I see what happened. I think you looked at the homework that he has given to the students in the course when he ran it, and then you looked at the practicals further down in the document. Now I can see it here.
Yeah, can you do the practicals?
Yes.
Yeah. I forgot. Yes. Like I did a few months ago. I'm sorry for that.
Don't worry, we got it now. We're all good. So this is where the plots come in. Here we go. And I think you actually took the same solutions from the same guy as I did here.
Yeah, they are awesome.
Like, they are. Yeah.
So we're in practicals.
So we can just follow the link here to get to this statistical rethinking. Medium 3. Sorry for everyone in the recording, by the way, for us taking this long.
Yeah. Okay. So let's see what he did. Okay, so he defines the probability of land given that you're on Earth, which is just 1 minus 0.7, so the land mass, so the water area. So everything that is not water should be Earth, so 30% or 0.3. The same for Mars, so the probability of that you're standing on land if you're on Mars is 1, because there is absolutely 0 water. So 1 minus 0 is 1. And now comparing the probability of Earth is the same, like it's the same probability than Mars, which is 0.5. There's just like these two options we have. And then we can use the Bayes theorem, which you have drawn perfectly beforehand, like the probability of Earth given land is probability of land given Earth times probability of Earth divided by probability of land, and we just put in the values here, which is 0.3 times 0.5 divided by probability of land. And we can directly see that we need to calculate the probability of land to solve this equation. And we can do this by using the conditional probability of seeing land and by just adding them up, so counting. The probability of land is the probability of land given that you're on Earth times the probability of Earth plus the probability of land given that you're on Mars times the probability of Mars, which is 0.3 times 0.5 plus 1 times 0.5, which is 0.65. And now we can add this to our equation, so 0.15 divided by 0.65, and we get the answer, which is 0.23.
Yeah. This is actually not the page that I got the solutions for that I then modified, but this one is much more beautiful than the one that I frequented. Oh, this is great.
I really like this.
I'm definitely going to put a link to this in an update email after today, so that everyone gets access to this right away, because this is just gorgeous. That being said,
I think the majority of these talks and these conversations are just talking about how pretty things are.
yeah. Well, I mean, Bayes is very pretty.
You've got to acknowledge it.
Yeah.
People are doing such awesome things. It's amazing.
Oh, so much work goes into good presentation of stuff. And I'm not even saying I do a good job at that. I'm just saying a lot of work goes into it. So going on to M4, we now change focus here. And we suppose that we have a deck with only 3 cards. Each card has 2 sides, and on each side is either a black or a white. Well, face, that is. One card has 2 black sides, and the second card has 1 black and 1 white side. So we have 1 BB, 1 BW, and 1 WW card, because the third card has 2 white sides. Now we suppose all 3 cards are placed in a bag and shuffled. Someone reaches into the bag and pulls out a card and places it flat on a table. A black side is shown facing up, but we don't know the color of the side facing down. Now we are supposed to show that the probability that the other side is also black is 2/3. We should use the counting method, as in section 2 of chapter 2 here, to approach this problem. That means counting up the ways that each card could produce the observed data, black side facing up. For this, I actually did draw this out. But first, I'm going to show the solution in the HTML with you guys. So M4 right here. Basically, we have the black card, the white card, and the white card. And for all of them, just given that we can see the first side that is facing up is black, we can assign likelihoods. So this isn't counting, but we can do counting here in just a second. Because the more machine-heavy way of doing this would be to assign the likelihoods. So the black card, there are 2 ways in which this could show a black side facing up at the start. The black-white card only has 1 way in which it can show a black side facing up to begin with, whereas the white card has absolutely 0. There is no way that placing the white card down, it will ever show a black side facing up. So we can then combine those likelihoods, multiply that with the priors that we have, which is there's an equal chance for any of them to be drawn, calculate the posterior, and it comes out to 2/3. Now, this should already be obvious from the likelihoods here, but if we were to count this, we would say the black card has 2 ways in which it can show black side facing up first, and then only 1 path after that, both of which equate to the other side is black too. So it stays at 2. There are 2 paths in which the black card will lead to black side facing up, and next side is also black. When we use the white card, there's only 1 way in which it will show black to begin with, but then white when we turn it around, because there is no way in which this could show black. It will always be black, white. So there's only 1 path in which we can have arrived at our first observation to begin with, but that path doesn't conclude to the end, what we want it to be. So 2 out of 3 paths lead to black side facing up once we turn it around. That making sense? For this, I can actually start the whiteboard because I'm not hearing overwhelming agreement yet. And for this, I am just going to say, this over here is our black card, where the first draw is definitely black and the second draw is also definitely black. Now after that, we have straight black draws, because there isn't, well, it's not necessarily a draw, it's a flip. So on the first draw, when we have our black card in hand, we see black here and black here, and then when we flip it, we see black here and black here as well. So those are two paths. Now, on the other hand, we can have our black-white card, and that can lead to, well, I could paint in white, but then we wouldn't see it. So I'm just going to add this here right quick. I thought I would get around drawing a lot. These are bees. You guys know these are bees. So basically, when we draw the black-white card, we can get black facing up on the first draw with one out of these two here. So this path is already not of any interest to us, because this is not what we're looking at. What we have lying on the table is black side facing up. So the conclusion of this path would be to flip it, and then it'll be white. However, this path doesn't get us to the desired outcome of our card being black-black. It gets us to our card being black-white. I'm not drawing for white-white because that'll immediately get stopped. So what you can see here is that we're only interested in this path, and this path. That's the sum total of paths that we need to consider, because they have the first side facing up be black. Everything else has first side facing up be white, so we don't even need to look at them. And now, just to get to the conclusion of these paths and see which number of these are successes, we just look at what happens when we flip them. And with that, we get a success here and a success here, but no success here. So that is 2 out of 3, 2/3. And that's how we would have done this using the counting method.
And for the next question, if you just add a BB card here, you get 4 out of 5 because you then add 2 paths.
Yeah. So basically, you would do this.
Yeah.
But I'm not letting you off the hook that easily, Gregor. The next question after that is yours.
You explained so well. So the next question is just that now suppose that there are 4 cards.
No, M6. You just answered M5.
Yeah, also M6, yeah, true. Imagine that black ink is heavy, and so cards with black sides are heavier than cards with white sides. As a result, it's less likely the card with black sides is pulled from the back. So again, assume that there are 3 cards. So this is just adding prior knowledge. So again, assume that there are 3 cards, black, 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 white, and white, white. After experimenting a number of times, you conclude that for every way to pull the black, black card from the back, there are 2 ways to pull the black, white card and 3 ways to pull the white, white card. Again, suppose that that the card is pulled and the black side appears face up. Show that the probability the other side is black is now 0.5. Use the counting method as before. So in our case, we added prior knowledge for this example. So previously the prior was flat prior with ones overall. And now the ways or the likelihood that the prior to produce each of these changes with black, black has a prior of 1, black, white, a prior of 2, and white, white, a prior of 3. And as we've learned before, we can basically add each of these to get the likelihood, to get the posterior, sorry. So the probability of having a black, black card, if the first card is black facing up, is if you have these pathways, a 2 divided by 2 plus 2 plus 0. So you have 2 ways to produce a black card divided by 2 ways to produce a black card plus 2 ways to produce a black-white card and 0 ways to produce a white card. So if you just look at these pathways, And at the end of the pathways,
I'm just going to draw them again right quick, because we had superfluous stuff in there, which unfortunately I couldn't just erase out of it for some reason. And also we are back to just 3 cards, right?
Yeah.
Yeah.
So these 3 cards for black, there are 2 ways to produce a black card facing upwards. For black, white, there's just 1 way. And for white, there is 0. And now we can update each of these counts with the likelihood to draw each. So 1, 2, and 3. 2 times 1 is 2. 1 times 2 is 2. And 0 times 3 is 0. And if we then put this into the equation for the posterior, we get 2 divided by 2 plus 2 plus 0, which is 2 divided by 4, which is 0.5.
Sorry, 2 divided by 2 plus what was it?
2 divided by 2 plus 2 plus 0. So the probability, so just
right.
the likelihood for B divided by all likelihoods, which is the posterior.
So this is 2 divided by 2 plus 2 like
plus
this.
2.
Yeah.
Plus 0. Yeah. Because we like just adding the white card.
Yeah.
Or the likelihood for the white card, which is 0. And this is 2 divided by 4, which is 0.5. So the probability, so the posterior probability for BB, black card, is 0.5. Does that make sense?
Perfect.
And just because I at least can change the colors, I'm just going to complete this. Yeah. And just to reiterate how I've done that in R, without wanting to steal any of your glory here, Gregor, what I've done is I have just simply changed the priors. So I still have 2 ways for black, 1 way for black, white, and still 0 for white. Those are the pathways we just counted. And then I just added the priors 1, 2, and 3, did the multiplication, and it comes out as 0.05. Sorry, as 0.5. Coolio. I am going to take us. Sorry?
Can you show the R code for a second?
Yeah, of course. Of course. So right here, I'm identifying the likelihoods as the numbers of paths we can take to get to the result that we're interested in. Then I just combine all of these into one vector, which has the same length as our prior vector, because that is the prior for how likely all of these different paths are. Oh,
we're still seeing the.
Okay. Thank you very much for telling me that. So apparently, whenever I share the whiteboard, it takes away the other thingy. Okay, now you should be seeing it. Sorry, I was on this the entire time. I'm totally sorry, guys. So this right here is what I've done for this. Yeah, I guess I'm learning Bayes here, and I'm learning Zoom at the same time. All right, that makes sense. Our pathways here 2, 1, 0, and our priors 1, 2, 3. Multiply them by each other, divide by the sum of what's in that multiplication, and we get our 0.5 result.
That's why I like code so much, because it just shows what I've tried to explain in such a confusing way with like 8 lines.
Oh, you did fine, Gregor. Code is just
so much better. Like, just look at it, it makes sense.
I like to think that we are preaching to the choir here when we say that code is just the superior method of explaining stuff. That being said, I'm taking us over to M7 here, and I suggest we go all the way to H4. And once we're done with H4, we take a 5-minute break just for tea and some chatting. And then we go into the practices for chapter 3 afterwards, just so we don't run completely out of steam. Coolio. Yeah, that gives you about 5 minutes, Sam, to look at the practices for chapter 3 and solve them. All right. I'm sorry for putting you on the spot. I know you can take it. So M7. M7 is assume again the original card problem. 3 cards, black, black, white, white, with a single card showing a black side face up. Before looking at the other side, we draw another card from the back and lay it face up on the table. The face that is shown on the new card is white. Show that the probability of the first card, the one showing a black side, has black on its other side is now 0.75. Use the counting method if you can. Hint, treat this like the sequence of globe tosses, counting all the ways to see each observation for each possible first card. So, I went straight into code again, and I'll gladly try the whiteboard here in a second. I just don't want this to go away. So basically, what we do here is we now use a former posterior as a prior. So we combine information. Because what we have here is that we know that there are 3 ways. Sorry, 3 ways? Yeah, sorry, I wrote it on here as well. Black, black is pulled first on either side. The next card is then white, white, either side, or white, black with the white side up. So that is 3 ways to get black as the first side, 3, and 2 ways with which the next card would be white side up, if that makes sense. I hope it does. I'm trying to draw this out here in just a second, then we can go back to the code as well. Actually, you know what? Let me just do that right away, because I think the code makes more sense once we have the visual representation. So I'm just going to go with the whiteboard. Gonna make this a bit bigger and clear everything in here. So basically, what we now need to count is the different draws that we can have. And for that, I'm just going to start in the middle and change this back to black. So we could draw, and this over here just represents the black, black card. First side up could be black, black, right? Now, the next path that I draw isn't going to be twisting it around, but the next path that I draw is the next card that I draw and what face this is showing. So this could be black if I draw black, white and have it black side up. It could be white, white. It could be white, and it could be white. So this is black, white, either side up. This is white, white, either side up. Same goes, of course, for this. And white, white. Now, the next path that we need to look at is drawing the black, white card. And here we have first side black up. Now, the next things we can draw is the black, black card either side up, or the white, white card either side up. Looking at the white, white card doesn't make any sense to begin with because we are starting with black is up. So we're not interested in those paths to begin with. So this is not of interest to us, neither is this, because this starts with the white side facing up. So what I do here is I count the paths. And we can see when we start off with a black, black card as the first one, then we have here 3 successes, here 3 successes, and over here, we have 2 successes. And that makes 8 in total. Whoops. Oh, drawing an 8 with a mouse is not my forte. Basically, we have this, which we can reduce to 3/4, which is 0.75, which is exactly what we were after. So now you can see what, and now it's probably not showing you my code. So just keep this in mind here, or take a screenshot if it helps. because I'm going to stop the share of this, take you back to the HTML. And now you can see there are 3 ways within which to produce the result that we want. Black side up first, white side thereafter for the next card. And these 3 ways are true for either side of black, black facing up. So we do 2 times 3. Make sense so far? That's just what we just had as our north-facing arms. Now for the east-facing arms that I drew for the black-white card, there are 2 paths which lead to the conclusion that we want, black first, white second. But these 2 arms really only show up once because they are dependent on the first side that is facing up being the black side of our black-white card. And with that, we get to that split of 6 to 8, which we then just plug with an uninformative prior into the calculation for the posterior, and then we get 0.75.
You know how we were just talking about how code made everything easier? That graph made the code easier. It made it so much more intuitive. Like,
yeah, no,
I think immediately an example of where the visual representation really helped. That was awesome. Thanks.
Thank you. I could tell that I myself was getting a bit lost trying to explain the code here. So I thought, you know what, flowchart, let's go back to it. And I am handing this over to Gregor again for H1.
Is it okay if you just keep on going for a second because I have to answer an email just really quick?
Absolutely, of course. So for the hard question here, and Gregor, we can also just make a quick break here if you want to listen to the explanation. We can just go on a quick tea break now.
I can just be on both sides. That's
cool. So the hard question here is: suppose there are two pieces. If there are 2 pieces of panda bear, this would be a very different question. There are 2 species of panda bear here. Both are equally common in the wild and live in the same places. They look exactly alike and eat the same food, and there is yet no genetic assay capable of telling them apart. And at that point, reading the question, I thought, well, why are we so sure it's 2 different species then? Never mind, that is what the question wants from us, so we're just going to run with it. They differ, however, in their family sizes. And to me, that sounds like plasticity and not like genetic variation that would warrant different species. But Sam, you probably know more about this since you work with life history stuff. So species A gives birth to twins 10% of the time, otherwise birthing a single infant. So probability of having a single infant for species A is 90%. Species, and the Italian guy who wanted us to scream probability doesn't exist is probably turning in his grave right now. Species B gives birth to twins 20% of the time, meaning 80% of the time it's going to be a singleton, otherwise birthing singleton infants. Assuming these numbers are known with certainty from many years of field research. Now, suppose you are managing a captive panda breeding program. You have a new female panda of unknown species, and she has just given birth to twins. What is the probability that her next birth will also be twins? So what we need to do to answer this is first figure out what's the probability that she is of which species, and then carrying that forward, so updating our priors, what's the probability that given our probability of which species she is, her next birth will be twins. And for that, we're going into the code. So the probability for twins in species A is 0.1. The probability for twins in species B is 0.2. We put these in our likelihood vector. We put our prior on it because we really don't know what's more likely here. And then we calculate posterior as prior times likelihood and do the sum of this. So for this, we now have our posterior, which the posterior is 2 values. The posterior in this case is the probability of belonging to, and I probably should have printed this on the page for the results, but the probability of being either in species A or in species B.
Okay.
Right?
Yep.
So now that we have this, we can again just times this with the likelihood and sum that up. because this is the posterior right down here in that last line is the likelihood of being in either species. And if we just times this with the likelihood of that species having twins in the birth, we get to probability that individual is in species A times 0.1, probability that individual is in species B times 0.2. We sum that together because we don't know exactly which species it's in, so we need to carry that uncertainty forward. And we then get to a probability of 0.16666 for the next birth also being twins, which is in between 0.1. So just to break this back to intuition, it's between 0.1 and 0.2, which are the two possible values that we have, which bound the interval within which we look for the true answer. And it's closer to 0.2 because having twins by itself makes the animal more likely to be in species 2.
Yeah.
That makes sense?
Perfect.
Coolio. And we can then go over to question H2. Recall all the facts from the problem above. Now compute the probability that the panda we have is from species A, assuming we have observed only the first birth and that it was twins. So for that, going back to the HTML, we'll use the same lines of code here again, but instead of doing that last bit here, where I sum the posterior times the original likelihood to get to the chances of the next birth being twins, I just look at the posterior right away. And I look at the first value of the posterior because that's the one that corresponds with likelihood of being belonging to species A. Make sense?
Yeah, it looks like question 2 should have been before question 1.
I think so too. I honestly think so too, but I think that's why it's in the hard section catalog.
Fair enough.
Because you expect it to build on each other, but in fact it doesn't.
I don't think, yeah.
Yeah, but yeah, with that, quite intuitively, you arrive at a probability of belonging to species A, which is lower than belonging to species B, because you have observed birth of twins, but species A has the lower probability of giving birth to twins than species B.
Yeah.
Cool.
Nice.
Gregor, I'm handing this over to you then for H3.
Yeah. So continuing on from the previous example, suppose that the same panda mother has a second birth and that it is not twins, but a singleton infant. Compute the posterior probability that this panda is species A. So I have no code for this example, just as a reference to the.
I'm just going to go over there.
Yeah, perfect.
H3 is what we were on.
Yeah, so it's basically using the same approach as you did. So we can just update your code with the new information. So the probability of a singleton birth, given that the species is A, is 1 minus the probability of twins, given that the species is A, which is 1 minus 0.1, which is 0.9. The same for species B, 1 minus 0.2 is being 0.8. And from then on, we can directly assess. So with the probabilities for species A and for species B, which we like, they stay the same. And then we can calculate the probability of being a singleton infant, which is the probability of a singleton given A times the probability of species A plus the probability of singleton given that the species is B times the probability of species B. And you just put in the values and get 5 out of 6. And with this, we can use the Bayes theorem calculate the probability of belonging to species A, given that it is a singleton. So answering the question and just putting in the values, we get a probability of 0.36.
Great. I am gonna go back to my code right here.
Yeah.
Just so we have the code answer as well. So there are two ways within which you can do this. I do it once with updating, and then you can do it just all in one step. So with the updating, I start again by so all of this should be able to run from scratch. This is why I repeat P twins A is 0.1, for example. So we have the likelihood for twins being born. Prior is which species do you belong to? 1, uninformative, we don't know. We calculate our posterior here, with our posterior being the probability of belonging to either species. Now our likelihood for the single birth, because now we're just looking at the single birth, is 1 subtract P twins A and P twins B from 1. Our new prior is our old posterior. So this is where Bayesian updating comes in, because we now have a better idea of what species this might be. We then just times prior times the likelihood that it's a single birth, and we just divide the posterior by the sum of the posterior, and we get to the likelihood of the single birth on the next birth being 0.36. We can also do this in one single update. If we just say probability of twins is 0.1, probability of twins is 0.2 for species A and B respectively again. Now we can also have the likelihood for twins and single being probability of twins in A times probability of single in A, which is just this path that we have. And we want to know the likelihood for this path given that it's species A, which is 0.1 times 0.9. With the path twins single for species B, we would calculate 0.2 times 0.8. So that would be the likelihood for this observed path for each respective species. And then we can just set uninformative priors or uniform priors, calculate prior times that combined likelihood there, and get our posterior with 0.36. Thus answering the questions answering the question that this panda is of species A. So again, just to point out, we're always in these cases looking at the first value of our posterior, because that one corresponds to species A in this case. If you wanted to look at the likelihood of this being species B, we would have to look at posterior square brackets 2 instead of 1. And now just going into H4 before we have a quick break here. A common boast of Bayesian statistics is that Bayesian inference makes it easy to use all of the data, even if the data are of different types. So suppose that a veterinarian comes along who has a new genetic test that she claims can identify the species of our mother panda. But the test, like all tests, is imperfect. This is the information you have about the test. The probability it correctly identifies a species A panda is 80%. The probability it correctly identifies a species B panda is 65%. The vet administers the test to your panda and tells you that the test is positive for species A. First, ignore your previous information from the births and compute the posterior probability that your panda is species A. Then redo your calculation, now using the birth data as well. So for this, jumping into H4, the likelihood of our test to have correctly assessed this as a species A panda is 0.8, because that's the correct identification rate for this, or 1 subtract 0.65, which is the true rate for species B pandas. Makes sense so far, right? Because the negation of I have correctly identified a species B panda is this is in fact a species A panda. And that's what we're looking at here. We then just set the prior of 1 and 1, because we don't have prior information for this first step of the exercise. We calculate prior times likelihood of our test being true, or of our test pointing to an A individual, not our test being true, but pointing to an A individual. We do our regular posterior calculation. We then again just look at value 1 in here because we're interested in species A, and we get a value of roughly 70%. So to a degree of roughly 70%, we can say that the test has correctly identified our panda bear to be of species A. Make sense?
Yeah.
Coolio. Now we want to add the information about the birth rates. And for this, we can just do the whole thing. So I assumed they wanted us to default to just the first birth was twins instead of twins followed by singletons. So I just went with, we have 10% twins for A, 20% twins for B. We put that in a likelihood. Our prior is now the posterior vector from the veterinarian. So this is that 70% rate for species A. We calculate prior, which we obtained from the veterinarian test, times the likelihood of the twins. We divide the posterior by the sum of the posterior. We look at the first value. And now knowing that the first birth was in fact twins, which is more likely to be seen in species B than in species A, our likelihood of our test actually having identified a species A animal here has decreased. Because we know, given their ecology, it is more likely that this should be a species B panda. And I think this is where I'm going to pause the recording, unless you want to mention something else. And we're just going to go on a quick 5-minute break here, which shouldn't show up in the recording. Resume the recording. And we're back. All right, after a short tea break here, we are going into the practice examples for, oh, excuse me, that really couldn't have come 10 seconds earlier. We are now going to go into the examples for chapter 3 in the McElreath Rethinking book. We are just going to go through these. Then I've got one more example out of the Introduction to Windbugs book that I didn't want any one of us to prepare for, so we could just solve it together. But it looks like it's going to be a very quick example, and then we're done. So I think we should be able to manage this in the remaining 45 minutes here. All right. Moving into the practice material for chapter 3, these problems use samples from the posterior from the globe tossing example. This code right here will give you a specific set of samples that you can check your answers exactly. So this I have just run on my end right here after having loaded the package and so on. And now we can, so I'm looking at the histogram of this too. This should be highlighted, but I guess I forgot to put a line break in here. For the sake of time, Gregor, are you fine with me just covering the easies, you covering the mediums, me returning for the hard ones?
For sure, yeah.
Coolio. I think that'll just move a lot quicker. Going back to this one. Use the values in samples to answer the questions that follow. How much posterior probability lies below p equals 0.2? And question 2, how much posterior probability lies above p equals 0.8? So for that, we just look at the sum of all of the samples for which it is true that 0.02, well, that the samples are smaller than 0.02. Because this will convert samples into a vector of true and false. And if we build the sum of this, it will just tell us how many trues are in there. So how many of our rings are smaller than 0.2. Now, we were asked for the proportion, so we also need to divide that by the length of the samples to then get to the conclusion. This all can be done, so this is the way he showed it in the book, but I personally prefer an easier way, which is just to take the mean instead of using the sum and dividing it by the samples, or dividing by the length of the vector, just take the mean. It results to the same in this case right here. Now, for everything that's bigger than 0.8, we do the same thing with the mean of the samples for everything that is bigger than 0.8, and we're done. That's as easy as it gets. I mean, we are in the easy questions, so I'm going to go rapid fire through them. And if there are any problems with it, stop me right away. Or if you think I am going through this too fast, but it's fine for you guys, but it might be too fast for someone in the recording, also then please tell me to go slower.
You were just taking integrals of a distribution, right? Just a different.
Pretty much.
That's
yeah.
Yeah.
Exactly. That is what. So I don't know if you got to chapter 3. Chapter 3 was all about summarizing posterior distributions. And this is much of what we're doing in these exercises here, which is also why it's a bit faster to go through. So first thing, or not first thing, but third thing we do here is to look at how much posterior probability lies between p equals 0.2 and p equals 0.8. For that, we can just look at the mean of all of the samples for which it is smaller 0.2 and for which the samples are bigger than 0.2 or small, well, and not or, sorry, and smaller than 0.8. This is just combining different logical statements in R, building the mean of that. That's our solution, 0.88. Going to E4, 20% of the posterior probability lies below which value of P, and then E5, 20% of the posterior probability lies above which value of P. And for this, we can just use the quantile approach, and we can just say, give me the quantile which contains the first 20% of samples, which then gives us that as a cutoff point of our samples. So 20% of all samples lie below this number right there. On the other hand, we can do that same thing for 0.8, and there we get to see that 80% of all samples lie below that value right there. That's as easy as it gets. So for 3E6 and 3E7, the questions are which values of P contain a narrowest interval, so that is the highest posterior density interval, HPDI, equal to 66% of posterior probability, and then E7 is which values of P contain 66% of the posterior probability, assuming equal posterior probability both below and above the interval. That's just the percentile interval. So that's where the distinction that I drew earlier in the summary comes in. And for that, we just use the functions from the rethinking package, HPDI, samples, 0.66. That's the values we get for that. And then samples with 0.66 in the PI function, we get these values. And we can already see we have a rather symmetric distribution on our posterior because these two intervals are very, very closely related to one another. And it's probably a toss-up between the two of which one you would want to report to summarize your distribution. So with that out of the way, I am handing this over to Gregor. I'm already going to scroll to your medium practices, and I am handing this over to you.
Yeah, for the medium questions, question 1. Suppose the cloak tossing data turn out to be 8 water and 50 tosses. Construct the posterior distribution using grid approximation. Use the same flat prior as before. So I was using tidyverse syntax, so the deepler package, where I first define our grid, which just goes from 0 to 1. So probability of, so basically no water to all water. And if using 20 grid points, I've seen used 1000 grid points, it basically makes the difference. And I was using a prior, a flat prior, so just wrapping 1 for the length of the grid or the number of grids. So in this case 20. And then I was calculating the likelihood, which is binomial, so either water or land. So I was using the deep binom function with 8 water tosses out of 15, and the probability is defined in our grid approximation, so a flat probability to begin with. From this, I calculate the likelihood, first the unstandardized and then the standardized likelihood, first the unstandardized likelihood, and from this, the posterior. Should be the unstandardized posterior and then the posterior. So I was using the wrong nomenclature, I'm sorry for that. And then you have the posterior, which you can plot using ggplot. And we can see that the median value is probably around a little bit above 0.5 for the probability, more or less normal distribution of the posterior.
Flipping you back to this.
So for the question M2, you shall draw 10,000 samples from the grid approximation from question 3 and 1, and then calculate HPDY. So we can do this with sample n, or in base R with a sample function. I was using sample n, using the distribution, the posterior distribution from the previous question, and we draw 10,000 samples with the posterior, with the weight equals the posterior of our post distribution. So this, I think it's the same with the base sample function. You have to give a weight for this as well.
Let me have a quick look at this. We are on M2 prob. You call it prob in that one.
So that's prob, yeah. Just different wording. And then we can use these samples. So values sampled from the posterior distribution. So now this is no longer a problem of integral calculation. This is basically data science. You can use the HPDY function from the rethinking package with 90% posterior density, and you get these two values, 0.31, 32, and 0.68. So the 90% HPDY is within these, this interval. And the next thing is just plotting this and highlighting the HPDY. So the HPDY in the plot is the red area.
I think it's really cool that you plotted this.
It makes it easier to visualize.
Yeah, no, this is great. Really, really well done. I like this.
The HPDY function, do you need to draw the samples, or can you do this without doing the sampling?
No, you need to do the sampling.
You need to do the sampling to build that. Okay.
The first one is just the distribution.
Gotcha.
The second one are real values.
Gotcha.
M3, go for it.
So M3, construct a posterior predictive check for this model and data. This means simulate the distribution of samples averaging over the posterior uncertainty in P. What is the probability of observing 8 water tosses in 15 total tosses? So again, we use the, no, not again, but for this we use the rbinom function to get real values, randomly sampled values from the binomial distribution. So previously we were using the binom function, which returns a distribution, but our binom just returns randomly sampled values from a distribution. So this is sampling. we sample 10,000 values, and we again give the weight or the probability by the p-grid. And the next one is just to, like the end frame, is just to give it a nice name. Plotting that is showing that the probability of observing 8 water tosses in 15 tosses, like, how should I say this? So this is basically showing, that's hard. So this is basically just, how should I phrase this? I'm having a brain freeze right now.
So
this is just a distribution, sorry?
The plot basically just shows you what the most likely outcomes are. But
it, at the same time shows it proportional to the probability of all other values. So not only for 8 out of 15 tosses, but if you would like to know the probability of 7 out of 15 tosses, so you would see it in this distribution as well.
Right.
And we can then just from this distribution, basically, we can just take out the 8 out of 15. So the middle block here with filter, and then summarize to get the proportion, so to get the probability. And the probability for this is around 15%, which is the most likely outcome, even if just 15%. But you can see that there are, like, it's not really likely to be 8 out of 15, but like it could be 7 or 9 as well.
Okay, moving us over to M4.
Yeah.
Sorry to just dump all of the mediums on you there. I just really think it's easier when we don't switch coding styles.
That's fine, yeah. I'm just like, it's getting late.
I feel you.
Using the posterior distribution constructed in previous example with 8 out of 15 tosses, now calculate the probability of observing 6 water tosses in 9 total tosses. 6 water lands, basically. Just the same approach. We define, we get 10,000 randomly sampled values from binomial distribution with the size 9, so 9 total tosses. And we define the probability or the weight with our grid. And we then filter, or we try to get the probability at 6 out of 9 tosses. So we filter for how many times it was 6, and then calculate the proportion by dividing the total number of 6 by all samples or all values, which is in this case around 18%. So the probability of observing 6 water in 9 tosses is around 18%. I'll try to rephrase this in a way. So we're basically getting 10,000 values, and out of these 10,000 values, we either get 1 or 2 or 3 or 5 or 6 or 7 or 8 or 9 for each toss. So if we want to get the probability for one specific value, we have to get the total number for this specific value from the distribution. The distribution has the size 10,000, and to get the probability then is to divide it by these 10,000, if that makes sense.
Perfect. I also just noticed I don't have to flip back and forth because you wrote down the questions there. Sorry, that's on me.
No worries. Start over at medium question 1, but now use a prior that is 0 below p equals 0.5 and a constant above 0.5. This corresponds to prior information that a majority of the Earth's surface is water. Repeat each problem above and compare the inferences. What difference does the better prior make? It helps, if it helps, compare inferences using both priors to true value of p equals 0.7. So we define our grid as well, and we use, just to have it in there as well, we define the old prior, which was a flat prior of just 1 repeated 20 times. And then we add a new prior, prior new, which is 0.5, which is 0 for all values below 0.5 and 1 for all values above 0.5. And then just the same approach as previously, the same process. We define our likelihood. So the density distribution for so we get a distribution from a binomial distribution with 8 out of 15 tosses, with the probability or weight given by p-grid, and we calculate the posterior for our old prior and for the new prior and plot that. If you just scroll down, you can see that with the new prior, the values below 0.5, so the probability of values of the true the probability that the Earth's surface has a proportion of water to land is, I'm sorry. So it's much likelier that the majority of Earth is land with the new prior. So the old prior has basically normal distribution with a mean value slightly above 0.5. And now the new prior has shifted this basically to the right side. So we have more water now, or probability that the Earth has water now increased. So we're getting closer to the real value, which is around 0.7 in this case, which is at least, so the probability for the value at 0.7 increased compared to the old distribution, the blue one here. Which means it's just like there's more space at the x equals 0.7 point. This just like visual checking shows that this is a better prior than the previous one if we know the true value of 0.7. But we can use the highest posterior density interval as well for this. And to use the highest posterior density interval, we need to use sampling as well. So we sample 10,000 values from our distribution, from the new posterior distribution, and fit this into the HPDY function. And our estimate for the highest posterior density interval is lies between 0.53 and 0.74. And the old one was, just to repeat this, was 0.32 and 0.68. So we can see that the new interval is way narrower. So we get more certainty as well as a better estimate. And the next one is just updating the example with the distribution for each value out of these 15 tosses, showing basically the probability. And then we can calculate this as well, getting these 8 out of 15 and summarize it, and we get a probability for 8 water in 15 tosses of 16%. Slightly compared to the old Prior. Just to compare to question 4 from the median questions, I was trying to get the probability of 6 water in 9 tosses, which is which is 23%, and the previous one was 18%. So this is quite a strong increase. For the next question, so it just shows that updating your Prior or using a different Prior with different values gives you a better posterior. So it can give you a better posterior, and just slightly playing around with your Prior and looking at posterior samples might make a big difference in how you lay out the model in the end. Just to get a feel of it. So playing around with the Prior is often quite a good idea, I think. Question 6, suppose you want to estimate the Earth's proportion of water very precisely. Specifically, you want a 99% percentile interval, so almost covering all of the distribution. Of the posterior distribution of P to be only 0.05 wide. This means the distance between the upper and lower bound of the interval should be 0.05. How many times will you have to toss the globe to do this? So this is basically a power analysis. Previous to making the experiment, you want to know how many samples or how many tosses do I need to get a really precise estimate for the value. So what I did for that is define one function that uses a grid, flat Prior, and then calculates the likelihood and the posterior, and finally the posterior interval, and then the total width, because we want to get to these 0.05 of the interval. So 0.05 difference between the lower bound of the PI interval and the upper bound of the PI interval. And what we put into this function is n, so the number of samples. So we can now set up a vector of samples. I just started with 20. If you scroll down, I started with 20 going up to 3,000. And to get the total, like I was assuming that there will be variance for lower values. So I was iteratively doing each calculation 100 times. For this, we need to repeat each sample size 100 times. And then using a map function, I was applying the function to each, applying these, how do they call the function, int_width function to each sample, and then plotted the values. And what you can see is on the x-axis the interval width, We wanted to have an interval width of 0.05, which is highlighted here in red. And we can see that for low sample sizes, we get quite a wide range of possible interval width, so a lot of variability, just as assumed. But we don't reach, or like we're for these low sample sizes, we just can't get a certain enough estimate. So we just don't know. There's too much uncertainty for these low sample sizes. If we increase the sample size, we get more certain about the estimate, and until, so up to 2000 samples should be enough to get an interval width of 0.05, and then increasing them up to 3000 even increases the certainty we get about the estimate, and we reach values below 0.5. So 2000 samples should be enough to get the preferred certainty for our estimate.
That graph is awesome.
I think Eric has the same graph.
I actually have the exact same solution, and I think that's because both of our sources were McElrath himself.
Probably, yeah.
Yeah, I know. I got my solution straight from McElrath.
Okay.
Yeah, no, it had gotten very late yesterday when I was preparing these, so I may not be as well prepared for these as I was for Chapter 2 exercises, because I blasted through them with some pre-made solutions. But now I can try to explain them to you guys, because I'm taking over for the hard exercises. And for the hard exercises, we get some ready-made data, which is actually already contained in the rethinking package, just as the data set called Homework Chapter 3. And hard question number 1 is, using grid approximation, compute the posterior distribution for the probability of a birth being a boy. So we have 2 birth strings in here, both recording firstborn and secondborn. So we want to compute the probability of a birth being a boy, irrespective of whether first or secondborn. And we want to assume a uniform prior probability. Which parameter value maximizes the posterior probability? So now we look at the point estimate here, which McElrath advises against, and I would back him up on that, but we do it for the sake of the completeness anyways here. So I load the data, I get my number of boys, which is the success in this sense, as the sum of births of boys in 1 and births of boys in 2, so firstborns and secondborns. The total number of samples that I have is just how many observations I have as firstborns and how many I've got as secondborns. Then I just look at my grid size. Here again, I'm going for 1000 grid because the computer had the time for it. And all of this calculated really, really swiftly. So now I run the sequence from 0 to 1, which are probabilities of a birth being a boy, and I want to estimate them in a grid with 1000 intervals, or 1000 steps in there. So then I set my prior to be 1 across the board, uniform, thus not very informative. And my likelihood is coming from a density binomial distribution here, where the number of boys in my original sample is the success rate. The size, meaning the trials for each of these success rates, is the length of the total amount of births that we observed in both first and secondborns, and the probability is just 0 to 1 on that grid that we drew earlier. So again, we calculate our posterior, then we standardize our posterior, and now I just plot the posterior. We get this kind of distribution. Now look at which value maximizes the posterior. We want to obtain the corresponding probability for any birth being a male. I'm already jumping ahead with firstborn here. And that is a probability of a birth being a boy of 0.555 in this case. So you can see it's not quite equal between the sexes here, and boys seem to be birthed more frequently in the data that we have. That does not necessarily mean that's true globally. It's just within the data set that we're looking at. So I'm going to go a bit quick here. Interrupt me if anything doesn't make sense, because I can see we're drawing close to the 4 p.m. deadline here. So on question 2, using the sample function, we draw 10,000 random parameter values from the posterior distribution we just calculated. We then use these samples to estimate 50%, 89%, and 97% highest posterior density intervals. And this is where I definitely should have visualized them, but I haven't. So what I do here is just, I take my 10,000 samples, I sample from this grid, right, from this grid of probabilities that we're looking at, with the probability being the posterior, replacement set to true. I get my highest posterior density interval for a value of 0.5 here, then 0.89, then 0.97. I also just put that all into a for loop so it would come out as just one block, because I thought that was definitely more helpful here. And we can just see how the estimates between these values really shrinks. Expands. Does that make sense? One second. I've got to wrap my head around this myself. Yeah. So the more weight that is supposed to be contained, or the more area that's supposed to be contained within your highest posterior density interval, the wider the interval will become. And that's why we're seeing these numbers change quite a bit. But it seems to have a huge issue with going below 0.05. So the highest posterior density interval really argues that there's a huge chance, or a huge certainty in our data and our model that births of males are more likely to occur than births of females. And I guess letting us compute multiple different HPDIs is simply just to show us how that widens the spectrum. But it might not necessarily widen the spectrum in both directions. That's what the PI would do.
Surprisingly,
That's awesome.
It does for me, like widens the total spectrum for me.
Does it?
Why?
Okay.
So
let's have a look at your code right quick.
Yeah. So my well, where do
H3, right?
Yeah.
No, sorry, H2 in H2.
So basically just the same approach, where we sample from the posterior with size 10,000. The probability is the posterior, replace equals true, and then we calculate the HPY at 50, 89, and 97%. As you can see, the lower threshold for all, so I get the 0.501 for the 89% HPDY, but I get different values for 50 and 97%.
That's interesting.
It is.
Because it really just goes over the. I'm just checking if my code is accurate here.
I mean, we have the same approach. No means like.
That is weird.
It is.
Could it be that we're on different versions of the rethinking package?
Probably. But I'm using.
Okay, I didn't currently reinstall, so it might be on my end. I'm going to do a clean reinstall of rethinking and see if that still persists, and then we can have a chat about this. I wouldn't want to do the troubleshoot right now, to be honest, because we're really quickly running out of time.
I don't see anything wrong. I'm just trying to find something wrong.
Yeah.
But I mean, given that the posterior is like normally shaped or bell-shaped, it
Yeah.
should get a lower value, a different value for each HPDI lower threshold. Does that make sense? Like, the same.
Yeah, it does. It does.
It would just make sense if we have like cutted distribution. If we just have a slope for the distribution and the HPDY just covers the right side of the distribution. So it should change, I think.
Yeah. I'm just going to have a quick look at this in my solutions here.
Yeah.
So I'm just quickly going to reload the rethinking package. And that's on GitHub. And somewhere here, it should already come with dev tools. Just gonna overwrite a few things here. Because that is very confusing.
It is. Yeah.
I'm not gonna up any of the dependencies, and I hope that works out in the end. I don't want to update dependencies, thank you. Yeah, I think this is, and this is definitely a lesson to take away from this. It would have definitely helped if I visualized this. Okay, so we installed stan R. Second, it skips this. So I am on the newest version of rethinking.
Okay.
That's interesting. I'm just quickly going to load it up here.
I'll just check.
I'm going to jump back down again. All right, we were on. Yeah, got our homework. Run this chunk. And then run the next chunk. Samples not found. Oh yeah, I may have run this on the wrong object, I guess. Because this is supposed to be on p_samples. I think this may have been me being on the wrong stuff. Yeah, that was me. That was me. I ran this on samples, which was an object that came from a different function earlier. So I'm really glad we found this because now I get the same values as you.
Perfect.
Crisis of
yeah, no, that was on me. That was just a typo on my end. A very nasty one. Good. Thank you so much for pointing that out. That was fantastic. No, seriously.
Things like this took a lot longer. That was a really quick fix.
Yeah, it's so good to be in a study group like this, seriously. Because I would not have spotted this. I would have just said, oh yeah, clearly works. So with that in mind, let's just quickly go through the last two hard exercises and then the introduction to WinBugs example we're just not going to do. I'll flash it on
the hour just because of a meeting, but keep going.
Yeah, I'll flash the other example on screen in case anyone wants to take a screenshot and solve it. But let's move on with this. H3, using our binom to simulate 10,000 replicas of 200 births, you should end up with 10,000 numbers, each one a count of boys out of 200 births. Compare the distribution of predicted numbers of boys to the actual count in the data, 111 boys out of 200 births. There are many good ways to visualize the simulation, but the dense command part of the rethinking package is probably the easiest way in this case. Does it look like the model fits the data well? That is, does the distribution of predictions include the actual observations as a central likely outcome? And what I've done for this is I've opened this up with NB trials, so birth trials, it's just 10,000. I'm setting a seed because I want this to be reproducible. I am generating random numbers from a binomial distribution with 10,000 trials for just these total births for each trial, being 200 in this case, and then p samples is just what I obtained up here. So that is what I already calculated the HPDI for and now correctly calculated for. But right here, the typo thankfully isn't in here. I then just look at the simple histogram of this. I can see that 111 actually isn't the highest peak, but somewhere further off to the right-hand side. I look at the mean and the median just out of sheer interest. And now when I look at the density of this, so I didn't go with, I actually don't remember what he wanted me to use. He wanted to use the dense command. And right here, I do use the dense command. So I use the dense command on my birth samples that I just obtained here in my simulation with the different probabilities that I sampled previously. And right here is where I've got my original number of boys, which is very much close to the peak of the density that I obtained. So this is doing fine, but not the best. I would definitely say this is adequate. Yes, there's that bump over here, but that might just be a sampling bias. So moving on to H4, hopefully we can manage this in the last, oh no, there's an H5 as well. So I guess we won't finish this with Sam still here, but we will finish this with just Gregor and I. So now we compare for H4 10,000 counts of boys from 100 simulated firstborns, only to the number of boys in the first birth, so birth 1. How does the model look in this light? So I go back to this. Now we have n boys that are firstborns. It's just the sum in birth 1. Total for that is just the length of birth 1. The trials that I will simulate for are again 10,000. Again, I'm setting a seed. I am now using the new total trials per, so the new total births that I look at for each trial, and still run with the same p samples that I obtained from my posterior previously. Drawing a simple hist, putting my line in here for where I actually observed data, and suddenly it seems to overpredict the number of boys. So this is what our model would predict. This is what we actually observed. And if we use the dense function here, we can see that the model clearly overestimates the number of boys in the first child due to a higher number of boys recorded in birth number 2. I can't see the chat, god damn it. I assume, Sam, you just typed something.
I was just saying adios. I was just saying adios.
All right. Have a good one.
Ya.
Bye.
All right, see you guys.
All right, and there it was only 2. Technically, we could switch to German now, but I guess we won't for the sake of the recording. So for H5, the model assumes that sex of first and second births are independent. To check this assumption, focus now on second births that followed female firstborns. Compare 10,000 simulated counts of boys to only those second births that followed girls. To do this correctly, you need to count the number of firstborns who were girls and simulate that many births 10,000 times. Compare the counts of boys in your simulations to the actual observed counts of boys following girls. How does the model look in this light? Any guess what is going on in these data? This is clearly about correlation between different sexes upon birth. So what I do here is I identify how many girls there were in the first birth string. Then I identify how many were boys following girls in the second birth string. So that tells me that there were 39 boys that were born after a first girl, with 49 total cases in which a girl was the firstborn. And you can already see there's a huge disparity here. So you can already tell a large predominant group here was males in the second birth following the birth of a female. And it always feels weird to refer to human babies as male and female, doesn't it? that's just on the record now. But with that out of the way, we can now look at how we calculate this stuff. So again, we take 10,000 trials. This time we only run those 10,000 trials for trial sizes each of however many firstborn girls we had. And we run that with the probabilities that we still have from our initial model, which was just looking at all of the births in one step. Now, when we look at the mean of this or the median, we can see that we would expect, according to our initial model, 27 males following the females. Now, when we look at that with a histogram and with our actual value, we can see that now we woefully underpredict how many males are born following females. So this means that the model underestimates the numbers of boys as a second child following a female firstborn. The conclusion to that would be that the gender of the second child, or sex, we should say, of the second child, is not independent from the first one. And that assumption in our model would potentially make our model very flawed for real-world applications. And that's that.
I just want to add that I get a different result for 3H4.
3H4, sure.
Like the model does fit my prediction.
3H4.
Where you...
All right, let's have a look at this. I am just going to do this bit right here. I'm just going to have them side by side.
Exactly. So this
H4. Got it. Let's have a look at that.
So start with 1.
Can visualize the results. D binom, you do H4. Why are you using a D binom and I'm using an R binom?
Good question. But to compute the likelihood, the likelihood is always a density. It's always a distribution, density distribution. But I'm not. Are you calculating the likelihood there? No, you just sample.
No. I'm trying to calculate, given the different probabilities, what the likely outcome is.
Yeah.
Doesn't our binom make sense here? Isn't that what we would do?
It does for your approach,
right?
Like, but if just like checking with Jeffrey Girard, he's actually getting the same result as I. So, but he's using your approach with our binom.
Maybe I've got a typo in here again. I wouldn't put it past me, to be honest.
No worries. Put it out there. But
no. This is great. This is really good because I know I was getting majorly tired when I worked on these yesterday.
Same.
So here he has.
There is like the code from Jeffrey Girard to yours. So just keep it like this for a second.
That's what I'm doing right now. Prob is P grid. That's my P samples. But he's running D binom here.
Yeah, but in the lower one, he samples from this with R binom. What are you sampling from? From B trials? What's B trials? Where did you define B trials? And B trials there. Thousands.
And B trials is right here. So this is where I'm simulating data.
Yeah.
This will probably be painfully obvious to us after the fact.
So it seems like you didn't update the likelihood for only first births, but you're using the same likelihood for all births. Could that be? Prop P samples. You defined P samples for all births.
Yeah, you're right.
but you're predicting for first births only.
You're right. You're right. I am using the all births. Let me quickly have a look at how the question was phrased again. Now compare 10,000 counts of boys from 100 simulated firstborns only to the number of boys in the first birth, birth 1. Yeah, I think I see what happened here. I think for me, H4 read as use this model that you got out of H1 when it could, and probably more correctly so, be interpreted as use the model that you used in H3.
I see, yeah.
And I think that is probably what happened here. So let me just quickly do the sampling from this one right here.
Yeah, you just have to update.
I'm just going to have a quick look at your code here. I'm not actually sorry. I'm not using tidyverse, so I'm much more comfortable with this one.
Yeah, of course.
So I'm just doing the same thing here, where I just take the sum of birth 1, then the length of birth 1, and this right here. I also have that p grid.
Yeah.
Lovely. So I'm just going to copy this stuff over just to see if I'm getting the same results here. And I should, just to make doubly sure.
Seems good.
Because there's our likelihood times the prior. Our prior is still uninformative.
Yeah.
Great. We build our posterior. Then we, I shouldn't have printed it. There we go with the posterior. Here we go with the samples. There's our density that we're looking at. And that looks exactly the same. Yeah. So now let me just
quick the question, basically.
Mm-hmm. Yeah, I really think this comes down to how you interpret the question, doesn't it?
Yeah, it does.
Yeah, because really it is just this part which then goes into, God, sorry, it is, so NB trials is B sample, 1 second. This NB trials right here. Probability is P samples. So basically this P samples, sorry, no, I'm still confused. Our binom, what he calls PPC is my B sample.
Yeah.
Then we have the NB trials, which is 1E4. We have this, which equates to 100.
Exactly.
Yeah, I just haven't run this yet, but this is 100. Yeah. And then my P samples are his samples, where he samples. Yeah, and that's the part that I'm missing here.
Exactly. You using the P sample from the
Yes, I'm using the P samples from previously. And with this,
yeah,
I am doing what the question commands of me.
I mean,
okay.
You would basically define a function which a model which predicts all births, and you then look at how it performs for only births. So you're basically defining the purpose of the model different from the research question.
Yes, and that's exactly what I thought was supposed to be the takeaway here.
Well, it could be. I don't know.
Yeah, no, that's question could be clearer, but it's cool to see that we understood the question in different ways and still both arrived at valid conclusions.
I have really big problems by referring to this code as a model. Like he refers to this as a model with discrete approximation, but for me it's like, no, this is not a model yet.
It feels weird, right? Yeah. I'm just going to stop the recording here. For everyone in the recording, Merry Christmas, Happy New Year and all of that. And hopefully see you in attendance in